So let's take a look and kind of talk about how we get these formulas for finding the area of a square cross-section and also the area of a rectangular cross-section. So we know that a square has all equal sides, so we could find the area by doing the base squared. That would be the same thing as doing base times base. And as we saw in the applet, and you can almost look in this graph here in this picture, we imagine all of these square cross-sections. So the length of the base is f of x minus g of x. And again, if I zoom out and just scroll over here, you could see that's how we're developing this area formula. So the length of the base is the difference between the two functions. And then to find the area, we're just going to square that. Now, for the rectangle, in a rectangle, the base and the height are not equal to one another. So for the area formula, we're going to just say, yeah, the base is, again, the difference between f of x and g of x. And then we're going to multiply it by the height. Now for this, you see this little asterisk here. So I put a note here that for rectangles, information about the height may be given. So for instance, it might tell you the height is 2, or it might tell you that the height is twice the base. All right, so what we're gonna do first is we're just gonna practice writing some of these volume equations here and basically setting up an integral that would express the volume. So for number 1, the base of a solid is bounded by f of x equals the square root of x, and g of x equals x cubed. So before I get too far into this, the square root function, I'm just going to highlight it in color code here, is pink, and our cubic function is blue. I like to do that just so that when I go to my graph, I can see now the upper function, that was the f of x, the lower function of g of x. You certainly don't have to color code. You could just label in there like I have here, but that's the idea. I also notice I have 2 points of intersection that are kind of bounding this area. So 0, 0, and 1, 1. All right, now that I have this, I'm going to set up my integral that basically expresses the volume of the solid where each cross-section is a square and is taken perpendicular to the x-axis. So when we're doing this, our volume is equal to, the bounds are going to be 0 and 1. Those are the x values that basically are the boundaries of that shaded region. F of x, our upper function, is radical x. The lower function is x cubed squared dx. So again, here, notice this is our upper function. This is our lower function. And we're squaring it because that's how we find the area of a square, right? So whatever you're filling in, if I just kind of shade this in for a second, whatever is going here should represent the area of the square. If I just scroll up to the beginning of our notes here, that's what's represented here by a of x. Now, part B for this problem is asking us to do the same thing, but now we're going to do it perpendicular to the y-axis. So when we look at this here, you could see, looking at the graph, if I'm going perpendicular to the y-axis, all of my squares are now going like that. And when we're doing that, if you watch the previous videos on how to find the area between two curves, we also need to get all of these equations in terms of y, which basically means x has to be by itself. So we were given y equals radical x. If I get x by itself there, I'm going to get y squared is equal to x. The other was y equals x cubed. So in that case, x is equal to the cube root of y. So what we're going to do is we're going to find our volume again. The bounds happen to be the same here, but really these bounds are the y values. So it's just coincidental in this problem that the points of intersection have the same x coordinates and y coordinates in each one, so 0, 0, and 1, 1. But these are technically representing y values. And then we're going to take the rightmost function, which in this case is the cube root of y, subtract the left, and we're going to square that and put dy at the end. So again, anytime we are doing cross-sectional volume perpendicular to the y-axis, we want to make sure that everything across the board is y's. So the bounds are y values, the functions have y's in them, we have dy at the end, and so on. Okay. All right, let's take a look at an example where we have to actually calculate the volume. So number 2 says the base of a solid is bounded by y equals 1/2 x squared, y equals 4.5, and x equals 0. Find the volume of the solid where each cross-section is a rectangle, where the height is twice the base. So I mentioned earlier in the video that when it's rectangles, you usually get a little more information about what the height is. So in this case, we know the height is double the base, essentially. And we're doing taken perpendicular to the x-axis. So what that would look like if I zoom in on the graph here, all of these little rectangles, we have to imagine coming three-dimensionally off of our screen, off the paper here. And we are going to, again, be doing these perpendicular to the x-axis. So they are looking like this. Now, when we find this, our bounds are going to be x values. So I can see that the points of intersection here are going to be 0, 0, and then 3, 4.5. So when I go and do my bounds, I'm going to be using the 0 and the 3. To represent the two functions, so this top function here, we could color code if we want, but this is our line, the y equals 4.5. This is our parabola. We can shade this part too and highlight it. But basically, we should all see in the picture that the upper function is y equals 4.5. The lower function is the parabola. So first thing I'm going to do is I'm going to imagine this being the base, right? So if this is the base, I can represent the base in this problem by 4.5 minus 1/2 x squared. So that is the base. The height we know is twice that, right? The problem tells us that. So I know the height is 2 times 4.5 minus 1/2 x squared. If you want to distribute that, of course you can. But that's the idea here, that we are going to have to look at this picture and determine how do we write the base, how do we write the height, because now remember what we want to do. We want to actually calculate this volume here. So we're going to go from 0 to 3. The area is base times height. Well, we said that the area, the base, is 4.5 minus 1/2 x squared. The height was 2 times that. And again, you may distribute if you'd like. And then we're going to put dx at the end. So we could clean this up a little bit. We could rewrite this as the integral from 0 to 3 of 2 times 4.5 minus 1/2 x squared dx. Okay, we could also pull that 2 in front of the integral. We could do a few different things. And then we can go to our calculator, evaluate this integral, and we're going to get for our volume 64.8. Number 3, the base of a solid is bounded by f of x equals x squared minus 4. So that's our parabola in the picture. And y equals 0, which is basically the x-axis. Right? You can see in this picture now that the upper function is the x-axis, the y equals 0. And our lower function is our parabola. However, when I keep reading, yes, we're going to be doing squares here, but we want it perpendicular to the y-axis. So that tells me I'm going to have to take this function and solve for x. When I do that, I'm going to add 4 on both sides. I'm going to square root, and I'm going to get plus or minus radical y plus 4 is equal to x. So if I go over to my graph, what I'm actually going to do is I'm going to take that parabola that I highlighted in blue, and I'm going to separate this. So I'm going to take this piece, I'll keep that blue, but I'm going to take this and make it pink, another color. The reason I'm doing that is because I want to identify the right function and the left function, and they are different here. So over here, this is x equals positive radical y plus 4. This is x equals negative radical y plus 4. So when I'm looking for the length of the base, since we're going perpendicular to the y-axis, okay, that means it would be crossing the y-axis, forming right angles, I'm going to use the rightmost function minus the left. So our volume here can be represented by negative 4 to 0. Remember, our bounds should be y values since this is perpendicular to the y-axis. And our base of the square is radical y plus 4 minus negative radical y plus 4. And since the base and the height are the same in a square, I'm going to square this and put dy. So I'm going to clean this integral up a little bit. So this is going to be the volume from negative 4 to 0, or is equal to negative 4 to 0, of And inside this parentheses, I'm going to have 2 times radical y plus 4 squared dy. I can clean that up again. And when I square what's in the parentheses there and simplify this, I'm going to get 4y plus 16 dy. And now we can evaluate this. So we can find the antiderivative. That would be 4y squared over 2 plus 16y. And we're going to evaluate from -4 to 0. That means that I'm going to plug the bounds in. So I'm going to simplify that, by the way, to 2y squared. And I'm going to subtract what I get when I plug in the -4. And when I do that, I should get that my volume is 32. All right, number 4, the base of a solid is bounded by f of x equals 4 minus x. I can see that's the upper function. G of x equals -x squared. That's the lower function. X equals 0 and x equals 3. We're going to find the volume of the solid where each cross-section is a rectangle with a height of 3 taken perpendicular to the x-axis. All right, so our volume in this case is going to go from 0 to 3. Those are our bounds. When we're finding what goes here after the integral symbol, it's whatever the area is. So we know that the base of this rectangle is 4 minus x minus -x squared. We know the height of the rectangle is 3. That's given to us, dx. We could also pull that 3 out to the front if we would like. And I could clean up what's in the parentheses here to 4 minus x plus x squared dx. And then we have some choices. We could either take the antiderivative, evaluate the bounds using the fundamental theorem of calculus, and get our answer. If we have our calculator, we could also evaluate using Math 9 in the calculator. And I'm going to get that the volume of this solid would be 49.5. All right, one last problem in this video. So the base of a solid is bounded by f of x equals the square root of x minus 3, y equals 0, and x equals 6. We're going to find the volume of the solid where each cross-section is a square taken perpendicular to the x-axis. So when I look at my graph, I can tell that the bounds are going to be 3 and 6. The upper function is radical x minus 3. The lower function is 0, so you could write -0 if you would like. And I also know that the height is the same here. So the base and the height are the same because I see the keyword of square. So I'm going to put squared here. Okay, if you want to rewrite it as radical x minus 3 times radical x minus 3, you could. And dx. So when I clean this up a bit, I'm going to get the integral from 3 to 6 of x minus 3 dx. And this one's a pretty easy one to evaluate by hand. So I'm going to get x squared over 2 minus 3x. And we're going to plug in the bounds. So I'm plugging in 6 and 3, and then I'm going to simplify this. So when I compute all of this and simplify that, I get as my area, as my volume, 4.5.